Hello all, we're going to do something called a titration now. As we go through all of this, remember the whole point of this exercise is to find the concentration of an unknown solution of sodium hydroxide.
And we're going to make a sodium hydroxide solution. There are our sodium hydroxide flakes. We're going to throw, that should be easily enough. And we're going to fill that with water. So let's fill that with water. And again, we're going to stir with a clean teaspoon. And this is not a standard solution of sodium hydroxide. You notice we haven't weighed it. Fine, so we close this, and now we're going to fill. And be careful you don't get the stuff in your eyes. Be careful with it. This funnel. Right, so now we're going to open this little tap, and we're going to watch till the level drops till naught. And just have a look how you can see the meniscus, or the rounded part of the liquid, is just touching the bottom, or the 0 mark. I'm going to just let out a fraction more. Okay, so that is now zeroed. Now we're going to begin our actual titration. So we take a conical flask or an Erlenmeyer flask. We're going to add to it just a tiny amount of phenolphthalein solution, or if you like, phenolphthalein powder, just a few drops or grains. So there's our phenolphthalein, and just the tiniest few grains of that. So there's barely noticeable amount of powder in the bottom there. Right, now we have something here called a pipette. And the pipette has a naught mark there, and it goes up to 25. So this is a 25 ml pipette. We're going to put the pipette into the oxalic acid. We're going to very carefully suck. On the pipette. Now notice that you've got to be careful that as you suck, you don't lift the tip out of the water, because then it's going to suck into your mouth. Then what we're going to do is we're going to slowly move my finger up to allow air in, and you will see the water level will begin to, the oxalic acid level will begin to drop. And I've got to do this as slowly as possible. And there I've got now exactly 25 moles of oxalic acid. And so I'm going to pour it into this conical or Erlenmeyer flask. And so there it's going in. I stir it around with the phenolphthalein powder which I added. So now that's completely dissolved. So now we are going to slowly open the tap and allow sodium hydroxide to come in and watch what happens. We're adding sodium hydroxide and we stir or swing the flask around. And we're going to add sodium hydroxide until there's a color change. Now look, do you notice that there's a slight changing in color? With each drop, it's beginning to form that slightly bluish, purpley look. Let me get something white behind that. So we're going to add some more sodium hydroxide and watch until one drop turns it. Do you see how I'm adding drop by drop? Do you see how that color stays there? But it still disappears as we shake it. So we're going to continue to add drop by drop. Now that pink purpley color keeps on disappearing, but there's going to come a time when it won't. One drop is going to be enough to make that color stay. And I think that we've hit our drop. So now that it's permanently that color, we now go and we have a look at the actual measurement and how much sodium hydroxide we've used. So we go and we have a look. It started at 0 and it went all the way down till, and there we are on exactly, I just want to see if you can see, exactly 26 moles. Right, folks, so today we're going to be doing a titration. Before we show you the video, let's just explain exactly what we're going to be doing. This is part of the grade 11 syllabus. In fact, if you have study and master, it's on page 185. So we're going to take an acid and a base. Now we're going to combine them in this conical flask. We're going to be pouring the acid from a pipette and the base from a thing called a burette that's got a little tap. We mix the two together. We put a little bit of phenolphthalein indicator in there, and at the moment it turns pinky purple. Then we know that the amount of acid cancels out the amount of base at the equivalence point, and we know at that point we have only salt and water in here. Now if we ran a little bit more acid in, it would then turn back to clear from its pinky purple, and if we add more base it'll just turn a darker pinky purple. So we wanted at that point where it's just turning permanently pinky purple, and then we know we have formed a salt and water. So an acid plus a base forms salt and water. So we're going to use oxalic acid plus sodium hydroxide. That's a weakish acid, strongish base. Look at the complicated formula. H2C2O4 with 2 waters of crystallization in the oxalic acid. We find that in spinach and 3-leaf clover. Sodium hydroxide, we find that in drain cleaner. So oxalic acid and sodium hydroxide forms sodium oxalate is the salt and water. So in the video we'll show you how we know the molar mass. If we added up all those elements, atomic mass comes to 126. We put in our own measured amount of 6.3 grams of oxalic acid. So that's the molar mass, capital M with a subscript A, small m with a subscript A, that's the moles of acid. The volume of the acid that we're putting in, here we're putting in 25 cubic centimeters or 0.025 decimeters cubed. And then we pour in our base, and we found the amount of base that we put in was 26 cc's or 0.026. And we found at that particular point it just turned permanently pinky purple from being colorless. So now we knew we had just salt and water, and now we're ready to find the ratios, first of all, that the acid combines with the base in a balanced reaction. So first of all, you can't do anything unless you balance the reaction. Now when you balance a reaction, you've got to know the ratios in which they combine. So maybe you've got to look up. I had to look up what oxalic acid was. I know what sodium hydroxide is. And look, we substitute the two H's for two sodiums, but the rest stays more or less the same. The water comes off, there's water, but more water forms when the OH combines with the H. So now look, there's one sodium on the left of the arrow, there's two. So my natural reaction is going to be to put a 2 there. Then I look at the waters. So those two OHs combine with those H2s to form 2H2O. There should be 2H2O. But there was also two waters of crystallization. So I know this is going to be the two that were formed when the acid combined with the base, and then the two waters that came off. And then if you look at that, you will see that it is actually a balanced equation. So complicated reaction, balanced equation. So what is the mole ratio of acid to base? We look at the coefficients, the numbers in front. How many moles of acid, how many moles of base? 1, that's the coefficient in front, is to 2. So that number is the N. That number there, that's the number of moles of base, is going to be 1 is to 2. 1 mole of acid will neutralize 2 moles of base. And now we go to this complicated looking formula, and it says number of moles of acid which you get from the reaction over number of moles of base which you get from the reaction. That's the coefficient. Coefficient is the concentration of acid times the volume of the acid, concentration of the base times volume of the base. And all of those are written down before, which we had worked out. So let's plug those values in. We're now knowing that 1 is to 2, that's Na upon Nb, equals, what's the concentration of the acid? 0,2 times, what's the volume of the acid we use in our pipette? Volume of the acid was 0.025 over, what's the concentration of the base? Well, that is the thing that we are trying to find out. So concentration of the base is a question mark.
So there we have our formula, number of moles of acid over number of moles of base equals concentration of acid times volume of acid over concentration of base times volume of base. Substituting in our values, there's our molar amounts, 1 upon 2 equals concentration acid times volume acid, concentration base times volume of base. Cross multiplying, don't forget we're trying to find concentration of base equals 0.01 over 0,026, and there is our final concentration of the base, 0,385 moles per decimeter cubed.